In this video, I will explain the selection criteria of the CT in terms of secondary current. As we know that there are two standard currents with reference to CT secondary, one is 5 ampere, one is 1 ampere secondary. So which one is better for our application? We will discuss today in this video. Current transformer or CT is a very basic and important component in power system networks. It is used to measure, to monitor and to protect the power systems. So in this scenario, selection of CT is a very important, and for CT selection, CT ratio is the most basic and very important parameter to choose. In case of CT, as far as the primary current rating is concerned, the user has no choice but to go for a primary current rating as close to the current of load. Let's say in our any circuit the current is 73 ampere, then we can go for the next high rating available. Standard recognizes some standard ratings in the world for the primary current, but when it comes to the secondary current, standard gives us two choices, either to choose 1 ampere or 5 ampere. These two are the standard ratings of the CTs available. So which one secondary current we should choose? Which one secondary current meets better our requirements? For this, let's analyze a case. Let's consider a CT having ratio of 100 ampere oblique 1 ampere. Means 100 ampere primary and 1 ampere secondary. This is CT ratio. This is a bar type. Let's consider that this is a bar type primary. Bar primary means one number of turn. So the ampere turns, when there is a 100 ampere current flowing through the CT, 100 ampere by one number of turn is equal to 100 ampere turn. Ampere turn, just to clarify, it's just a flux, magnetic flux. Let's consider a coil having n number of turns connected to a voltage source. Current flowing is I. Then current multiplied by number of turns, it's a flux. In any transformer, primary ampere turn must be balanced by the secondary ampere turns. In our case, we have chosen 100 oblique 1 ampere CT. To achieve balance ampere turn, we need 100 turns on the secondary. 1 ampere secondary multiplied by 100 turns, there will be 100 ampere turn that can balance the primary ampere turns. Let's consider that if this would be a 100 oblique 5 CT, 100 oblique 5 ampere CT ratio, and the same scenario, 100 ampere flowing through the primary, bar type primary, so 100 into 1 turn is equal to 100 ampere primary, 100 ampere turns. When the CT is 5 ampere, it means that 5 into what number that will multiply and equal to 100 ampere turns to balance out the primary ampere turns. This is the 20. It means that for the secondary, in this case, when we are choosing CT with 100 oblique 5, only 20 secondary turns are required. 20 NS are required to balance out the primary ampere turns. Look, there is a big difference in the number of turns. In one case, when with the 1 ampere CT, the turns were 100 numbers. When we have chosen the CT with 5 ampere, number of turns reduced up to only 20. So to accommodate 20 number of turns, a smaller core is obviously required to accommodate. While to accommodate 100 number of turns, a big core area is required to accommodate 100 number of turns. So the first difference is the core size. Core size. With 1 ampere CT, core size was almost 5 times higher than with the 5 ampere CT. This is the first difference that we have observed so far. So up to this point, we have observed that with the 1 ampere CT, core size will be much bigger as compared to the 5 ampere CT. This is the first outcome of our discussion. Secondly, as we know that the EMF equation of transformer induced EMF in the secondary is equal to, or we can say it's directly proportional to 4.44 flux N and frequency. This is the voltage induced. This is basically the EMF equation of the transformer. From this equation, we can see that the EMF induced is directly proportional to the number of turns. As the number of turns in a CT with 1 ampere secondary current is more, as we have just seen here, in case of 1 ampere CT, it was 100 turns on the secondary. So this equation implies that the EMF induced with the 1 ampere secondary will be higher as compared to the CT having 5 ampere secondary. Higher voltage implies higher insulation required to insulate the secondary winding. So second outcome of our discussion is that higher number to accommodate the higher voltage, higher insulation will be required. Once the insulation is more required as compared to the 5 ampere case, it means that the CT winding area will increase. A big CT, basically the CT size will increase. While in case of the 5 ampere CT, again 100 by 5 ampere CT, as in this case the 20 turns on the secondary are required to balance the ampere turns on the primary and secondary. So while there are 20 turns, the EMF equation again implies that a very small voltage as compared to the 1 ampere. Small voltage means small insulation means small size. So up to here we came out with the two results, that with the 1 ampere CT, the core size will be higher as compared to the 5 ampere CT. Similarly, the voltage induced in the CT with 1 ampere secondary is also higher. Higher voltage means higher insulation required. Higher insulation means the size, higher size and higher price. Same is the case with the core. Big core means big price, big size. So it seems that 5 ampere CT is far superior as compared to 1 ampere CT. But then there is a question that if 1 ampere CT is not so good as 5 ampere CT, then why standards are recognizing 1 ampere CT? To analyze, let's discuss one more case. In the second case, let's assume that CT and a relay panel or relay is located far away from each other. Like CT is located in some grid yard. This is CT, and it's connected through interconnecting cables up to the relay panel located, let's say 100 meter far away from the CT location. The distance, this is the interconnection cables, 100 meter length. In this case, basically the CT load will be 1 from the burden of the relay, which is nowadays for the numerical relays, digital relays, modern relays, it's a very small, let's say 3 VA, 5 VA, the burden of the relay. But now these interconnecting cables, which is 100 meter, and let's say that the size of this interconnecting cable is 2.5 mm square. Let's assume that the distance between CT to relay panel, the resistance or the burden of the lead, let's say its resistance is 0.8 ohm. Then the burden imposed by these interconnecting leads will be I square into R. I, which is 5 ampere CT, so secondary is 5 ampere rated, 5 square into R 0.8. It comes out with 20 VA. So now our CT is basically loaded with two loads or two burdens. One is the burden of the interconnecting leads, which is 20 volt ampere. Second is the relay. Let's say relay burden is 5 volt ampere. Then the total burden on the CT will be 25 volt ampere. In this case, we can move or we can choose the next higher burden ratings available. Let's say the next higher standard rating is 30 volt ampere as per standard available. So we will proceed, we will move with the 30 volt ampere. Now imagine that actual load was only 5 volt ampere, but due to location, due to interconnecting leads, we are moving towards 30 volt ampere to feed 5 volt ampere basically actual load. Now we are feeding 30 volt ampere. 30 volt ampere means that the bigger CT, bigger price. More burden, 30 VA will also impact size, cost, weight. So in this condition, CT with 5 ampere secondary would be costly. And the advantages so far we have discussed with 5 ampere CT, 5 ampere secondary CT looks like lost. We have lost the advantages discussed so far in the case when the CT and relay panel are located far away. Let's consider that the same load is being connected through a CT with 1 ampere secondary. Then the lead burden will be I square into R. I square will be the 1 ampere into square into 0.8. It will be equal to 7.5 VA. So with the 1 ampere CT, the total burden of the interconnecting leads is 7.5 VA, while in case with the 5 ampere secondary, it was 20 VA. So there is a big difference. Now with 1 ampere CT, the total burden will be 7.5 VA from the leads plus let's say 5 VA from the relay, which will be equal to 12.5 VA. So there is a big difference between 30 and 12.5 VA because this burden of the CT is directly impacting the cost. So to conclude our discussion for today, we can conclude that whenever CT is directly or very close to the relay, whenever CT is placed very close to relay, like in the same switchgear where relay is mounted, then 5 ampere CT will be the best choice. While whenever there is certain distance between CT and switchgear or relay, the 1 ampere CT will be the good choice. I hope that this discussion will clarify you the basic concept for the selection of CT secondaries.